How's it going, everyone? Hope y'all are doing alright today. Do you have any questions on anything before we get started? I'm doing pretty good. We're getting through this thing. It's almost Thanksgiving already. It's a little cold today, though. Okay. So today we're going to continue working on section 7.2. Just picking up from sort of where we left off on Monday. But we just want to do some more problems utilizing the calculators to solve these different problems. Let's see. We're going to start with number 38 on page 375. The reading speed of 6th grade students is approximately normal, with a mean speed of 125 words per minute and a standard deviation of 24 words per minute. Okay, so initially we establish what the mean and the standard deviation are. From there, we answer the following question. Now, let's go ahead and skip A. We're going to start with question B. Find and interpret the probability that a randomly selected 6th grade student reads less than 100 words per minute. So this is B. Probability that reads less than 100 words per minute. Okay. Now, this is our data value, x. Okay, so x is 100 in this case. So the first thing we want to do is convert our data value to a z-score. And this is kind of what we finished with on Monday, is utilizing the z-score formula, x minus mu over sigma. Okay. So we'll plug in x is 100 minus mu 125 over sigma 24. Now subtracting, that's negative 25 over 24. And so we calculate that. And again, we round to 2 decimal places because we know this is going to keep going. This is a repeating decimal, but we'll go ahead and round this to negative 1.04. Okay. So we have our z-score, and let's construct a graph now that illustrates what's happening here. We know that for our standard normal distribution, right in the middle we have 0, and so our z is to the left of that, negative 1.04. And because we want the probability that a randomly selected student will read less than 100 words per minute, less than would tell us in this case, we want the area to the left of negative 1.04. Okay. So now what we've established is that this area is equivalent to the probability. So we need to be able to find that area using our calculators. And again, we could use the back of the book as we looked at on Monday. That means we need to establish what is the lower bound and what is the upper bound for our shaded area. The lower bound is always where the left, how far left it goes, and the upper bound is how far right it goes. Because we want to make sure we get those in order. If we get them out of order, it's going to give us the wrong answer, even if we have the right numbers. It may give back an error, or it may give back the opposite of the answer. So our lower bound is negative 10. Good. Because we know that this will just keep going and going, and so we like to use negative 10 as a lower boundary. Good. And upper is negative 1.04. Right. So with this information, we have enough that we can put into our calculators. I'm going to use the 36 here. So second and data. Go over to distribution, and we want normal CDF. Excuse me. Now for the mean, our mean is 0, and sigma is 1. When we change to the standard normal distribution, we always use 0 and 1 for the mu and the sigma. Our lower bound, we said negative 10, and our upper bound, negative 1.04. And so we go to calculate, and we have our answer. This one we want to round to 4 decimal places, so that'll make it 149. That'll round up to 2, 1492. Okay, so the probability that a randomly selected student, the 6th grade student, I guess, reads less than 100 words per minute is 14.92%, or 0.1492. Is everyone okay with that? Again, on the 83s, we would go second and vars to get the normal CDF prompt. And on this one, we would have to do our lower first, comma, and then our upper, which I did put a negative, good. Then comma 0 and 1 for the mean and standard deviation. And we should get the same result as we do here. And then again, if we have an 84, it's a combination of those two things. You do second and vars to get to the normal CDF, and then once you get into that, it'll prompt you like the 36 does, as we saw. So it's kind of the better hybrid of the two of those things. Okay. I won't keep showing this on both calculators, but I wanted to kind of remind everyone, in case you're going through it on your calculator right now as we practice these. I think that's a good opportunity. Just so you can make sure that you are able to enter it and get the same correct answer. Also, it's nice to kind of practice that a bit so that you will have a better memory of how to do it later when it comes time to take a test, for instance. So definitely recommend that you kind of practice using the calculator alongside what I'm doing here. Okay, let's continue on to part C. And part C says, find and interpret the probability that a randomly selected 6th grade student reads more than 140 words per minute. Okay. So similar situation, except now it's more than instead of less than, so that'll come up in a little bit. But this is our data value x right here, 140. And so we want to set up our z-score based on that, which is 140 minus 125 over 24. So we end up with 15 over 24, which is 0.63. Okay. Let me move this up a little bit more. Now 0.63 is positive, so we know it's to the right of 0, so we'll draw it over here. There we go. Now, more than 140 words per minute means we will shade to the left or the right. To the right. All right. This is it's the when it says less than or more than, it's really not that confusing. The ones you have to watch out for, I think, are at least and at most, because I know those are ones that some people have struggled with. In earlier classes, and yeah, but yeah, just pay attention to the language, and that way we can correctly choose the side to shade, and then correctly calculate the probability. So our lower bound, what would that be? Go ahead and put both boundaries. Yeah, 0.63 for our lower boundary, and 10 will be our upper, since it keeps going to the right. Okay. So second data, distributions, normal CDF. 0, 1, and then 0.63 and 10 are those are our bounds. Calculate. So you get 2.264, and then it'll just be a 3 because the 4 won't round it up any. Okay. And so that's the probability that a randomly selected 6th grader will read more than 140 words per minute. Now we could also say that that's the proportion of 6th graders that read more than 140 words per minute. 26.43% of 6th graders are expected to read better at a better level than that. So it could be interpreted in two different ways. Whether we're looking at the probability of a random individual, doing a certain thing, in this case, reading above a certain level, or it also refers to the proportion of the population that we would anticipate reads over that certain level based on this data. Okay. So we'll continue to part C. No, that was part C. We'll continue to part D. And again, mu is 125, sigma is 24. Just write that down again. For part D, we want the probability that a randomly selected 6th grade student reads between 110 and 130 words per minute. Okay. Now, this time we're given two different x values, two different data values. So one of them is 110 and the other is 130. So what that means is we'll have to create a z-score for both of these values. So for x equals 110, z is equal to 110 minus 125 over 24. Subtract the mean and divide by the standard deviation. So that is negative 15 over 24, which is negative 0.63. And then for x equals 130, we repeat this process. 130 minus the mean 125 over standard deviation 24. So it comes out to be 5 over 24, which is, don't know that one off the top of my head. At least not the exact number. Let's do 0.21 there. And so again, the 8 rounds it up to a 1. Now, the nice thing here is that whenever it's between two values, these are our upper and lower bounds already, so it's really not a whole lot of guesswork here in that case. Okay. So, negative 0.63 would be somewhere around here. And positive 0.21 would be closer to 0. So somewhere there. We want the area between, so of course we'll shade between the two. But yeah, that's our lower bound and our upper bound right there. Lower bound is 0.63, negative 0.63. And our upper bound is 0.21. So we can use that data to put that, or those values to put that into the calculator. 0 and 1. And then 0.21 for upper. Yes. Calculate. 3188. Okay. So almost 32% of 6th graders should be reading between 110 and 130 words per minute. And so the chance that a randomly selected individual, or randomly selected 6th grader, reads between those levels is the same value, 31.88%, about 32%. Okay, any questions here? And our last part here is, would it be unusual for a 6th grader to read more than 200 words per minute? Okay. So would it be unusual? Now, what unusual means from a statistical standpoint, unusual means less than 0.05 probability. Okay? So basically, we have to calculate the probability that a 6th grader would read more than 200 words per minute. And if that number happens to be less than 0.05, then yes, we would say it's unusual. Okay, so a little bit extra layer to this question. But let's proceed with that. Again, that's our x value, 200. So we'll calculate a z-score, 200 minus 125 divided by 24. It's going to be like 3.13. Let me see. 75 divided by 24. 3.13. If I knew the answer, I should have just gone with it. Anyway, it's a pretty high z-score actually. Anytime we get over 3, it's probably going to be an unusual probability. It's kind of a weird statement to say. Probably going to be an unusual probability. Anyway, so draw our normal curve, which is an increasingly bizarrely shaped. 3.13 is actually pretty far to the right, and then it says more than 200 words per minute, so we'll shade beyond that to the right. Oops, side of the other frame. Okay. What is the lower and the upper bound for this particular graph? Upper is 10. And the lower is 3.13. Okay. So we put that into the calculator. We have 3.13, 10. 0.0009. Well, that is definitely less than 5%. That's less than 1%. So yes, it's unusual. So these would be our extremely gifted students reading over 200 words per minute, or else they're, what do you call it? Well, it would be speed reading, yeah. Anyway. All right. That takes care of that question. So we're also going to look at number 42. This question is on light bulbs. General Electric manufactures a decorative, crystal clear 60-watt light bulb that it advertises will last 1,500 hours. Suppose that the lifetimes of the light bulbs are approximately normally distributed with a mean of 1,550 hours. And a standard deviation of 57 hours. Turn the page for the question. Notice there was some extra numbers they gave us in the beginning of that problem that we need to kind of overlook and make sure we're actually finding the mean and the standard deviation, because this specifically states those. So question A, what proportion of the light bulbs will last less than the advertised time? Now, if we go back to the question, it says they advertise their light bulbs will last at least 1,500 hours. So we want to figure out the probability or the proportion that lasts less than 1,500 hours. Okay, and that's what this question is asking us. So this is our data value x, so we'll convert it to a z-score. X minus mu divided by sigma, so negative 50 over 57 and I can make that negative 0.88. Quite see that. There you go. I had my face in the way. Okay, so we've calculated our z-score. And so let's look at the graph here. Negative, we know, and again, in the middle is 0, so negative 0.88 is to the left. And we want the proportion that lasts less than this amount, so we'll shade to the left of that. So we'll use a lower of -10, upper of -0.88. We'll put that into our calculator and find the probability, or proportion in this case, which is really the same thing as far as how our calculation goes. Okay, I'm going to calculate, and so that is 0.1894. So almost 19% of the light bulbs would actually fail prior to beating that 1,500 hours guarantee. And so what that means is if they're going to how should I say this? If this is a and not really with light bulbs would we do this, but maybe with other things that are like have a warranty attached to them, maybe appliances and electronic devices that are a little bit more expensive than a light bulb. You anticipate a certain failure rate just from parts being not as good, or individual components going bad in the device. But like even in your car, you might have a warranty on it. If you bought it new, but things go bad and you'll need to get them changed. But on a device like this, or like your phone, for instance, that might be a better example. They only extend the warranty, 2 or 3 years on a phone, because if they go much longer than that, there's a higher chance of failure, and they know within 2 years there's a comfortable level that they would have to replace. Usually less than 10% for a lot of companies. Other companies may be more comfortable replacing less than 5%, and so they may give a shorter guarantee as a result. Anyway, it really depends on what the company is comfortable with. If they mean to replace anything that's under their guarantee. It's incredibly difficult to prove that a light bulb only lasted 1,400 hours before it burned out. So, and they're cheap enough that we wouldn't realistically do that. But if GE was offering guarantees on their light bulbs, and they know based on this that there's a 19% chance almost that they would have to replace a light bulb because it did not last how long they said it would. But again, kind of a silly example, because we wouldn't actually have a guarantee like that on light bulbs. GE can go ahead and say, yeah, it'll last at least 1,500 hours, and the majority of the time that'll be correct, and most people won't even notice, but if it burns out early. And there are things that, when we do have a warranty, that they are interested in setting a warranty duration that means they won't be replacing a lot of their devices, just a smaller amount generally. So, anyway, so what I wanted to, well, actually, let me do one or two more of these. What proportion of the light bulbs will last more than 1,650 hours? Okay, now again, that's our data value, x, 1,650. So we plug it into our z-score formula. We get 1,650 minus our mean, 1,550, over our standard deviation, 57. So it's 100 over 57. And so it gives us 1.75 as our z-score. Okay. So sketching our normal curve, 1.75 is certainly to the right of 0. Probably a little further than I've drawn it there, but that's okay. Why am I shading right here? If it says more than, it should shade to the right. Sorry. Okay. So our lower is 1.75, and our upper is, we'll just use 10 for the upper value in this case. Alright, so 0, 1, 1.75, 10, calculate. So 0.0427, yes. So only a little over 4% of their light bulbs will last longer than 1,650 hours. Alright, now I want to introduce kind of an alternate way that we can ask these questions. I'm going to keep using this light bulb example though, so I'm going to write down U and sigma again on the other side, or the next page, apparently. Okay, 14, not 14, that's 42. 14 is a factor of 42. I was mentally in the right place, sort of. Okay, so let's turn this question around a bit, and for this problem, I'm going to show you again on the book and then both calculators, because it is a little bit different on each one, as it always turns out to be. So we know that previously the company has advertised that their light bulbs will last at least 1,500 hours. Now, from what we saw in Part A of 42, that meant that about 19% would fall under that 1,500 hour mark. So my question is, what number would GE need to advertise so that only 10% of its light bulb would fall, would last less than the advertised time. Okay. The key thing here is 10%. Okay. 10% is actually the probability. So we want to find the value where the probability that results from it is 10%. So here's what we're working towards. We have some unknown value here where the area is 0.10. Okay. But this time we don't know the z-score and we don't know the data value x. Now, if we're using the book, it's actually slightly more complicated than if we were using the calculators, but and that's why it tends to be using tables like that. So what we have here is actually the area, and we could actually make that 0.1000. So what we would do is we'd go to our tables, okay, as we see here, and we want to find in the body of this table this 0.1000 value, and then we'll backtrack and get the z-score that attaches it, or that is connected to that value. Okay. So what we're doing is called a reverse lookup, because we're getting our answer here and then backtracking to the value that gives it to us. Now we go through and we try to find where we get that 0.1000 value. And let's see. We look right down here. It looks like it's falling between these two values. Now, usually we just pick whichever one is closest to 0.1000, which is the 0.1003. Sorry. And if we go across, this is negative 1.2. I'm sorry, you can't quite see that. If we go up, it's 8. So negative 1.28. We just go across and up to create that value. Okay. So this would be z equals negative 1.28. And that's the one that gives us the value closest to 0.1000. Now, that's our z-score. How are we going to get our x value? Well, we know z is equal to x minus mu over sigma, and we have the value for z, and we have the value for mu and sigma, so x is the only one that we don't have. So what we'll do is we'll change this so that x is equal to sigma times z plus mu. Okay, so you can essentially solve this formula and solve for x, and instead of having you do it, I'll just give you this formula if we need it. Okay. Now again, this is only if we use the book do we need to use this formula, because the calculators will actually give us the answer straight off. Sigma is 57, Z is 1.28, and mu is 1,550. So we take 57 times 1.28 plus 1550. And so left off the negative. That's one problem. What I just found is the top 90%. Alright, so let's try that again with the proper negative in there. 57 times negative 1.28, and then add 1550. No, so that's 1477 right at. So what we're saying based on this is that GE can say their light bulbs will last at least 1477 hours, and that means only 10% of their light bulbs would fail to last that long. So basically that means 90% of our light bulbs would actually meet that guarantee that they're offering. Now, the reason they don't do that is because it sounds weird to say this light bulb will last at least 1,477 hours. And that's probably why they would go ahead and just say 1,500. It's still over 80% of the light bulbs meeting that requirement, but it's a round number is a little bit more encouraging, I guess, or less suspicious might be a better way of saying that. If a company said this will last at least 1,477 hours, you start to wonder what happens exactly at 1,478 hours, I guess. If they gave us such a specific number. Anyway, they could go the other way and say at least 1,450 hours, but at that point we're down to like 5 or 1% actually. Not lasting long, which is a good guarantee, but yeah. Okay. Well, that's how we did it on using the textbook. We had to look up the number, but let's look at the calculators instead. The calculator requires 3 numbers: the mean, the standard deviation, of course, and the percentile. Okay, and so essentially, with wanting to know, what number they could advertise where only 10% would last less than that advertised time, essentially we're looking for the 10th percentile. So mu equals 1550, sigma equals 57, and we have the 10th percentile. Okay. So, in the calculator, though, we use the second data, and we choose option 3, which is inverse normal. Okay. The second data, or distributions, I skipped that part, sorry. And we want option 3, which is inverse normal. And what inverse normal does is basically reverses the process. Instead of starting with the data value and finding the probability, we're starting with the probability and working backwards to find the data value. Now, it's pretty easy in this case because the area, we'll use, this is our percentile is the area, 0.1, or 0.10 if we like. It'll truncate it to 0.1 if we do that. For the mean, let's go ahead and use 1550 and the standard deviation 57. And there's our number, 1466.95, so it rounds to 1477. Okay? It's much easier in the calculator, as always. Now, the 83s, of course, we have to be a little more careful. We do second vars. Inverse normal is still a third option here. It's a very specific order we have to enter the numbers in. And actually, I'm not quite sure I remember, but I think we enter the 0.10 first, and then the mean, and then the standard deviation. And these are all separated by commas. That was correct. It does, Jacqueline, and thank you for asking, we're looking at the left tail because we're looking at the lowest 10%. Hey, do you get the same answer with that? Excellent, good. Okay, but yeah, we see we get the same answer 3 different ways here, so as long as you have one way that we can arrive at the answer, that's great. Any questions on this? So another question we could ask, what number of hours represents the 75th percentile for these light bulbs? So that means our 75th percentile means the area to the left is 0.75. $7500 if we're using the table. So I'm not going to use the table again. Let's just no, we can use this one. Used to be this was the only one I used, but now it's my least favorite. So, anyway, it still does the job. That's fine. So second distribution, inverse normal. And so we put 0.75 first because we have the 75th percentile, comma 1550 for the mean, and 57 for the standard deviation, close parentheses. And that means that 1588.4, so about 1588 hours. 88 hours. And so that would represent the 75th percentile for these light bulbs. Okay. So whenever we say percentile, percentile already implies the area to the left or left tail, depending on how your calculator likes to express it. The 36s automatically do to the left, and so does the 83. That's actually a nice feature. You can choose left or right or center on the 84s, but probably won't make use of the other features. Okay. Any questions on these? Now, that wraps up that section, and that's as far as I got in my other class. I seem to remember it taking a little bit longer in the other class than we did today. I guess they had more questions at the beginning or something. I forget what happened. I might have started late. No, I thought I started on time. Anyway, doesn't matter. But we'll wrap it up there today. Let me give you some homework to practice, and again, I strongly recommend that you work on this assignment. What was that? Oh. Let's see. I'll be honest, I forgot what the assignment was, but thankfully I wrote it down for my online class. So on page 375, look at 39, but skip E and F, and then 41, 47A, and 49A. Okay. So 39 and 41 have like 3 or 4 parts that we want to do each, and that's just finding those different probabilities, like between or left or right of these given data values. 47A and 49A are the percentile questions, so they'll give you an opportunity to try those out as well. So again, definitely recommend that you'll practice those and make sure you're okay doing that. Do you have any questions still? No? We have time left if we do. That's all I'm saying. Okay. So today's Wednesday, so we'll continue with we'll start chapter 8 on Monday, and we'll continue from there. So have a good rest of the day, and I'll see you next week. Have a good one. Bye.